talking about it as well, right?
Oh, yeah.
Good. Yeah.
I mean, first we're
Yeah.
going to be talking about how it works, and then we'll actually show it working, hopefully.
That works.
Are you ready? Okay,
Yes.
great. So we're Team 7.
All right, good.
We're Team 7. My name is John Paul Arroyo. This is Eddie Escobar. And our project was in situ friction analysis. Go ahead. So our objective was to be able to test the coefficient of friction of different polymeric fibers, or to make a machine that can do so. We wanted to use a method called the twisted strand method, which is what you see right up here. But our mission, more or less, was to use this method, but to miniaturize it in order to place it into a vacuum, which would improve the results of it and also make it SEM compatible. People can run this test all over the country if they wanted to, but this test that you see up here, but the problem is that the results vary depending on location, because the coefficient of friction, or friction can be, the friction can be changed, or the results can be changed due to, temperature and different properties of.
Okay, what you want to say is friction can be dependent on those variables and this variables.
Okay.
That's a better way to say it.
That sounds a lot nicer. Okay. Next slide. So this is the current ASTM standard, very similar to the previous picture you saw. How this test works is that you have a spool of yarn, and it's pulled by the yarn take-up, and so it goes to the yarn guide, and they have an adjustable input tension, which can be an actuator, linear actuator, or something basically you can use to increase the tension of the fiber. It goes through a few tension gauges. It goes through a tension gauge where you can measure the input tension. And right about here, what you see here is the yarn helix, which is, this is why they call it the twisted strand method, where you take the fiber, and for this experiment, you would wrap it 2.5 times. This is where the friction will be occurring. It would simulate the friction occurring in,
Use a laser.
Friction occurring in woven fabrics and such, so it's more of an accurate reading than just taking 2 pieces of string and rubbing them together like a violin. So it would go down this pulley up here to the output tension and back to the yarn take-up. And we want to be able to make a machine like this, but smaller, and where the spool and the yarn take-up spool can be interchangeable. So when the yarn package is done feeding the fiber, we can just, and when the yarn take-up has taken up all the fiber it could, you can just switch the yarn package and the yarn take-up. It can be interchangeable more or less. That's what we want to accomplish.
So the take-up can become the package.
Basically, yes. Okay.
So say it that
I have to
way.
make it more concise.
Yes. Just trying to help you so you can perfect your presentation.
Absolutely.
Hope you're making notes of those comments.
Absolutely. So, like I said before, if it's going to, if this is going to run through an SEM, in order for the image to be, verifiable, the box itself has to be conductive, and the material we decided to choose was aluminum because it was a very light metal. And it also, and the components within the machine must be vacuum compatible as well, because the SEM is like it's 500, almost like $500,000, and you don't want to cause any damage to the machine itself, and also the vacuum chamber won't be able to completely close if the components aren't vacuum compatible. This is the equation that we'll be using to find the coefficient of friction. As before, I mentioned the input tension and the output tension, or the mean input tension, the mean output tension.
I don't see the laser.
It's kind of fading. I don't know. It's maybe low battery. I'm not sure. But it's right here. We also have the apex angle, and then the number of wraps which would be 2.5 times. 2.5 times around the lower pulley. And with these components, we'll be able, or with these variables, we'll be able to find the coefficient of friction of, let's say, if we're using Kevlar or
This is
some kind
mine.
of polymeric fiber. Oh, I was wondering where that
Make sure you
other
get it back
laser
to
was
me.
coming from. All right, go ahead to the next slide, please. Ed. So these are the, I already mentioned the improvements we could make. We can reduce the size of our machine, and we can improve the mobility. So you see we were able to walk around with our machine right here. We can make it more cost effective. There's another machine that they have that's very, provides the same results, but what it is, it's more like a miniature MTS machine where it has 2 clamps and it would just pull on the fiber. I say more cost effective because this machine right here is around $40,000 to $50,000, and you'll see very soon that our machine is considerably lower. I say more consistent results because this is a testing method with the use of vacuum and SEM. You can come out with more accurate results with your friend in Pittsburgh or Pennsylvania. And then and our machine will have potential for SEM imaging as well. So as you are running the test and looking at how the fiber behaves within the helix, you can actually have a good microscopic view of it. Go to the next slide. This was our proposed design that we saw, that you saw in Senior 1, where we had the pulleys of the fiber on top. That has changed. Go to the next slide. This is not our actual final design. This is something we had just for today. But we will have our pulleys here, our lower pulley here. A servo arm will be placed in this pocket in order to increase the tension. And the yarn take-up and the yarn package will be below in the interior of the box. Go to the next slide. So this is what we've had. We just have to install everything. We'll be installing everything today. Next slide. Okay, go ahead. Yes.
All right, I'm going to be talking a little bit about the components that we selected to place inside of our device. First of all, we have these 2 servo motors. Well, we changed this one to a different motor. But this is the one that is responsible for adjusting the input tension. It has a little aluminum arm onto which we attached another pulley right here. So we can control the movement of that arm to either increase or decrease the tension on the yarn as it's going around. This is the actual motor that replaced this one. It has a little pinion right up here, so it can interact with this metal gear down here. This metal gear is going to be placed on top of one of the spools. Whenever we're done taking up all of them, you can remove that, interchange the spools, and then put that gear back onto the other one. To control this arm right here, we have this servo controller, the servo driver. That's what we can actually use to adjust the tension. And then these are the small pulleys that we're going to be placing on top of our box. Here we have a breakdown of all of our material costs. It goes everything from the sheet of aluminum that we purchased all the way down to the little screws that we use to mount on top of it. After adding all of the materials together, plus the cost that it took for us to actually manufacture this box, we came up with a total of $701 for materials. A little bit about the manufacturing process. We began, like I said, with a giant 1-foot squared piece of 1/4-inch thick aluminum plate. I used a vertical mill, a cutting bandsaw, to cut them down into relatively shaped sizes. Then I came over to the milling machine to fine them down until their exact sizes, the sizes we were given in our original design. Any edges that came off of that, we would grind it out. These are some of the sorted hand tools that I use throughout the manufacturing process. And for the interior components, we're going to use a lathe to get them down to size. There's going to be little pegs and spools. So obviously for the round components, we have to machine them using a lathe. This is a breakdown of all the labor that went into designing this. Again, I repeated from going to cutting the sides down all the way to installing components and finally preparing the product and having everything ready. We're estimating that it would take about 23 hours to do, and given a manual hourly labor cost of $15, we came up with a $345 total. Obviously go ahead. Obviously, if you were to try to manufacture this yourself, it would probably be a lot faster, but since this is a design course, we wanted to make this with our own two hands. So if you want to reduce costs, you can easily reduce it right here. Next. Again, these are more of the components that we used. We're using some aluminum mounting brackets to have the servo motors inside stay in place. These are just the screws that we use to put everything together. We use socket cap screws for the outside, and these plain screws for the inside, or for the pulley. For future improvements, we came across a lot of different challenges across the way. The first one being that our final product is a bit too heavy to be placed inside of an SEM. So our first goal would be, for future designs, to make the machine lighter. Right now we are using 1/4-inch thick plates. Obviously that makes it too heavy. We can easily cut that to half the size. We can use 1/8 of an inch, maybe even more, depending on how it might work. Another challenge we had was trying to find a tension gauge that was small enough to fit onto the area where it's designed to test the tensions. So further research has to be conducted into finding tension gauges that would actually fit in there. And finally, we have to test the vacuum compatibility. We attempted to contact the manufacturer of the motors and the servo motors and everything to see if the components were indeed vacuum compatible, but they were unsure about it as well. Usually because the motors are for a hobby or recreational purpose. So we'd have to conduct more research to determine that. We obviously don't want to try putting it immediately into an SEM because we don't want to risk damaging a piece of equipment that is valued at over $500,000.
So the world's a very dangerous place. And they use composite body armor. They have to, let's say, the military and around the world, many different, police departments or basically, military. They use. I would think they would find use of. Sorry, I'm a little tongue-tied. So our machine, if in the use of our machine, I have to prepare this part better. The use of our machine and finding the coefficient of friction, this can help analyze such fibers as Kevlar to help improve such products as soft composite body armor that can possibly, save a life.
Well, I think what you want to say there is because of the global use and application of various materials for which this kind of product could serve, you need to do certain things. I think that's basically what you're trying to say.
I got a tongue tied.
By conducting research using this device, we were able to better enhance the quality of these
There you
materials.
go. And get the word global in there.
Yes. Next one. So athletic gear, it's $1 billion enterprise, and I think our machine can also help improve the quality of products in the athletic community.
And then there you can branch off and bring in some of the athletic uses globally.
Exactly.
Like in Britain, what they use this for tennis, for soccer, and so on
Exactly.
for the US, that kind of stuff.
Okay. And one more slide. So also commercial clothing, there's a lot of wear on our fabrics, and I think with our testing we can improve the quality of the clothes, and I'm sorry, I have to improve this part of it. I'm a little lost right now, but
You don't have a lot of time to do it.
yes, I know. But yes, we can improve. I'm sorry. We can improve the quality of clothing, military applications, concerning composite body armor, and also applications for sporting gear as well. So, but that's about it. Are there any questions?
Yeah, well, obviously you recognize that you need to do some improvement there.
Absolutely.
Technically, the changes in that friction arm and how it could impact the friction of the yarn seems a little vague there, and there's a direct correlation between the two. You're going to have more friction if the tension is greater. So, I mean, where do you optimize it? Where do you standardize that friction arm versus measuring the frictional, the mu in that whole device? You follow what I'm saying?
Yes, yeah, I do.
So that's a technical issue that you need to try and quantify, resolve, or come up with some kind of correlation that can be repeated consistently.
Yeah. I would think in that equation though, it may,
No, there's no variable in that equation, so that's what I'm saying. Well, go back and let's look at that. Yeah. Where's the variability in that equation?
The variability comes from both the tension that you put into it, actually, we got T1, and this angle right here, the apex angle. The whole point of the adjustable input tension is so that you can change the tension going into it, and by changing that variable, you'll have a completely different answer. Another thing that we wanted to do, notice how this apex angle right here is the angle made between the space over
The
here
alpha, yeah?
and right there. So what we wanted to do for our design was to incorporate a little slot right here where you can adjust that pulley here in the middle, so you can adjust that angle, whether you want a small angle like that or a larger angle like this. And-
Okay, so how does that correlate to a certain frictional value that is repeatable?
I'm hoping that when you do increase the tension, that you would still get the same coefficient of friction and
Yeah,
things
that's a
would
hope.
cancel out.
And this is engineering.
And- No,
so,
I know, and what I'm hoping is to find a tension gauge, actually a handheld one, and actually run a test to see if we get the more consistent
Because
results.
you're
we
going to be
have.
taken to task if you can't tie that down. This is an engineering thing now, not arts.
Yeah, absolutely.
So you need to be able to quantify it and provide specific guidelines so that this thing will be repeatable and the results will be accurate. So that there's got to be some correlation
Exactly.
between the tension
Our-
and alpha and input tension, output tension, alpha. Those are variables that you need to be able to predefine so that you can get a predetermined mu.
I mean, we wanted to leave it open. We wanted to leave it adjustable so that people can change it as they please. If they
I
want to.
understand, but
Yeah.
you need to
Show.
produce some kind of a
Yeah.
table that shows the variable and the
And showing
predicted
what-
value of mu.
Yeah.
And showing what each one would do.
Exactly.
Yeah, where
Okay.
that was one of the things that
Because after all, this is engineering.
Exactly.
You're coming up with a device that is
Exactly.
We're
going
going to come up with a table showing what each variable would alter in the overall.
exactly
Exactly right. You got it.
we can do that.
Equation.
All right. Now, the other thing is, bring up your two cost
Not bad.
charts. You got one cost there, and bring up the other one, and that cost. Why don't you somehow combine the two?
Well, I mean,
Or,
this one was just to go into detail, but we did add the labor cost down here. That's all.
yeah, but they're not together, they're separate, and I think you really want to get cost on the one umbrella.
I mean, our total cost is right there. We just wanted to break it down and show you the steps that we took, because people can see, oh, it took 23 hours, but what did you do in those 23 hours? And that's why I wanted to show, okay, this is how I
Okay,
divided.
so what you do is on that overall, you put a parenthesis where you have that 345 and say C, whatever that on the chart is
See, labor
labeled.
breakdown, okay.
Does that make sense?
Yeah.
All right. Because when you show that slide, it didn't show the connection between the two. This is why I'm raising the question.
Right.
So on that chart, you need to show the connection.
Okay.
So a parenthesis,
Parentheses,
labor, where it
C,
says labor
breakdown.
hours, and C production
See
costs.
production cost.
Exactly right.
Okay.
What about division of labor? There's two of you. Who did what? Or, I mean, was the labor or the effort in this project split 50%?
In terms of manufacturing, I was the one that took care of that, and in terms of research and report writing and the other things, he was in charge.
So I have a slide that demonstrates that,
Okay.
Okay.
that
A
the division
responsibility.
of labor was equal.
Okay, responsibility.
Yeah,
Okay.
and try and demonstrate that in your presentation as well, so the
This is
presentation.
supposed to be a teamwork.
Exactly, so division of labor has got to be defined,
Okay. So right after this, put division of labor.
or even before that.
I wasn't with him all along the manufacturing process, but he just has more of an expertise on it, so I didn't want to cut my finger.
I mean, but still, I mean, you cannot be blindsided or something. So that's what the IABs, they don't like. If one is working on this and one is,
No,
and then
yeah.
they don't have any connection.
Yeah, and
it's
then,
not considered
you know,
a teamwork.
you don't have to feel obligated to have him branded as the material guy and you as the soft guy, the research guy.
Yeah, the
He
manufacturing.
could be 60%, 40% on the manufacturing, you could be 60%, 40% on the research and the write-up and all of that. It
So
still
it's
shows
preferable
a
to
division
have-
of labor.
It's preferable to have both people involved in every step of the process, just have one involved more.
More, yes.
Something like that, so you can show balance.
Okay.
Does that make sense?
Yeah.
So if you go to 60-40, say you've got the project divided up into manufacturing and design and research, then one of you should be 60-40 on one side and the other guy should be 60-40 on the other side. As a number, it could be 70-30 as well.
70-30.
Yeah,
All right. Makes sense.
all right. Other than that, I think you're good to go.
And you need
So-
to prepare for the presentation.
Yeah.
The clients are looking for words which is not.
Yeah. You don't want to show up at the IAB fumbling like that.
Absolutely.
And also make sure your GLI piece, yeah, I think you have it there, you just need to brand it and label it.
Yes.
Okay?
Great, thank you very much.
Do you appreciate that?
Oh,
Yes,
absolutely.
it's been very helpful, thank you.
And we should include the timeline too, shouldn't we?
How much time did it take them?
They took 14.
The presentation was 14 minutes.
Okay.
But
So
you
that-
said you're going to add few more.
You've got a few other things, plus a demonstration.
Does-
I mean, we can leave
I
the
mean,
demonstrating
like,
in the meantime.
Would this be able to connect to there, so that way we can show the face, that we can actually conduct the test with this video
No,
right
we
here,
don't
or
want to
no?
change those.
Okay,
back
don't
and
worry
forth.
about
Don't worry about it, we'll
Okay.
figure out a way to have it there.
Okay.
It takes your
Or we
time,
can
not
have
our
the
time,
video
so.
Yeah.
on the slide, too.
So
We can include
So
audio up here too.
You were 14 minutes with what you did today, so bear in mind how much time it's going to take
Yeah.
to set up and demonstrate, because all of that effort needs to be within 15 minutes.
And I think if I don't fumble my words and I have something like really planned well, it's gonna go a lot smoother and quicker, so maybe we'll probably end like at 12 minutes or 10 minutes, you know? 'Cause a lot of the time.
But
is
all
spent
I'm
me
saying is,
fumbling,
whatever
yeah.
you do to tweak your presentation, remember
Yeah,
you
keep
got to
it.
throw that in there, and that needs to be within the 15 minutes.
Okay, great.
All right.
Sounds good.
Okay.
Or 2 to